So again, I welcome you all in this video. In this video, we will see the special cases of buck converter. So in the previous video, we have seen the buck converter with a pure resistive load, pure R load. And for that case, if we draw the input and output voltage relationship, so let's say this is the input voltage, which is the constant since it is a DC voltage with respect to time. And if we see the output voltage waveform, so the output voltage waveform is depends on the switching. So when the switch is on, there is the output. When the switch is off, no output. Switch is on, output. Switch is off, no output. So in this way, and this output, the magnitude of this output is the same as Vi. So this is the T on, and this is the capital T, and this duration is T off. So this was related to previous video. Now, when the nature of load is RLE, so this is the special case. So, the L, since L is the energy storing element, this is the energy storing element, and if it presents in the load, so what it do? The Yes. So L stores energy in the form of magnetic field, and it does not allow sudden change of current. It does not allow sudden change of current, which is being flowing through this. And after getting fully charged, it will try to find the path to discharge itself. So let's say I'm designing a step down chopper or the buck converter with the RLE load. So let's say this is R, this is L, and this is the E. So this is a kind of DC motor load. So this is the R, L, E, and this is the input voltage, and this is the chopper. Basically this is the chopper switch. So what happens when the chopper is on? So let us draw its duty cycle here. So let's say this is the input voltage, this is the input voltage Vi, so it is the constant with respect to time. So what about V naught? So when the chopper is on, all the voltage is appearing across this load, which comprises from RLE. So V naught is equal to Vi. When the switch is off, when the switch is off, then what will happen? Let's say at this moment, the this is the 0 and this is the T on, and from here to here, the off duration is there. So what will happen? Now, this L is getting charged during the on period. Now, what this switch is saying, no input voltage is there, means no current can flow through this L. But the tendency of L is not allow sudden change of current. So earlier, let us draw the current waveform also. So if I draw the current waveform, so due to this L, current was gradually rising. So let's say current was rising like this, and at this moment, this cycle is saying current just go to zero position. But this L will say no, 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 I will not allow sudden change of current. So this is to avoid such kind of difficulty, we generally place a freewheeling diode here. And this freewheeling diode will automatically activate when the inductor has to discharge. Now, where inductor will discharge its energy? So it will discharge its energy to this R in the form of heat. So during the off period, the inductor will get discharged. Again, when the on time is there, so the output voltage appears, and gradually the current will gradually rise, and then current will gradually decrease. So in this case, we have to let's say discuss to this value and this value of current. Let's say this is the maximum value of current and this is the minimum value of current. So how to calculate the value of this maximum minimum value of current? Let us see. So let us divide the time zone. The first mode of operation is from 0 to T on. Let's say this is the first mode of operation. So what is happening? The switch is on. So we can write uh, switch is on. So all the input voltage is appearing across the output, and output comprises from R, L, and E. So we can write directly this Vi is equal to the output. The E is there. Then I naught into R, the voltage drop across this resistance, plus Now, what is the voltage across this L? So, by formula, it is L di by dt. L di naught by dt. Now, we know this is the exponentially rising nature of current, and we have certain key equations for getting the nature of this exponentially rising nature of current. So let's say we are finding the I naught value, which is varying with respect to time, and it is for this exponentially rising nature, there is the universal formula for getting these type of equations. It is the I infinity, that is the final value, plus I 0 minus I 0 minus I infinity into e to the power minus t upon tau. So this is the formula, universal formula. And now we have to put the values for everything, like what is the tau, what is the I naught, and what is the I infinity. So first of all, the tau is the time constant. The tau is the time constant, and its value for any RL circuit is L by R. So its value is L by R. And I infinity, so I infinity means when the what will happen when this L will fully charged. So that is the I infinity. So when the L will fully charged, it will act as a short circuit, and the current flowing through the load is basically now R and E is there, and this is the VI, and this is the direction of current I naught. So what is the what we see in case of t tends to infinity, the fully charged L, and this I infinity is basically VI minus E upon R only. So the I infinity is Vi minus E upon R. This is the final value of current. And what is the initial value of current? I 0. So when the time is 0, the I is I minimum. We can see from the figure. So I 0 is basically I minimum. So let us put these values. Let us put these values here. So it will be I naught, or we can say I naught, which is the function of time, is equal to Vi minus E upon R in place of this one, plus I naught. So in place of I naught, we can write I min minus Vi minus E upon R into e to the power minus t upon tau. So in place of tau, you can write L by R. Okay. Now, in this equation, we can also write like at like we are having some boundary conditions from this figure. So we can see this is the T on, and this is the capital T. So we can say at T is equal to T on, the this I naught is what? It is the I max. So we can write here at T is equal to T on, the I naught T is basically I max. If I place that value here at t is equal to t on, so it will be I'm exclusively writing for t on, so it will be I naught for what? T on. It is equal to I max, and the value of I max is nothing but Vi minus E upon R plus I min minus Vi minus E upon R, Vi minus E upon R into e to the power minus. Now here you need to take care, in place of this t, you can write t on upon capital tau. So this is t on upon capital tau. So this is I'm writing once again, the I max is equal to Vi minus E upon R plus I min minus Vi minus E upon R e to the power minus t on upon tau, t on upon tau. So this is the I max. This is the I max. You can either write it as Vi minus E upon R by taking it common. You can write 1 minus e to the power minus t on upon tau, and plus I min e to the power minus t on upon tau. So this is a fixed value. This is the fixed value of I max because this is not the function of small t. This is we are having the fixed value of t on. We are having the fixed value of tau. So we can calculate the maximum value of I max. And similarly, in case of mode 2, the time is from t on to capital T, and in this case, the chopper is off. So the current flows through the freewheeling diode because we have seen here. So in this period, now no input voltage is there. So the current will flow by the energy stored in the inductor. That energy will contribute to maintain the continuity of current in the load, and it will maintain the property of L also. But that current will flow through this freewheeling diode, and we can see when this freewheeling diode will work, there is a direct short circuit appears across the load terminal. So in this case, what is the load voltage? Since the short circuit is there, so load voltage is zero. So we can write directly the 0, and other side we can just write Ri naught plus L di by dt plus E. So again we can write the universal equation for I naught here. So this is the I infinity plus I naught minus I infinity into e to the power minus t upon tau. Now this I infinity. So in this case, let us say this is the case. This is the direct short circuit, and this is the R. This is the let's say this is E, and this is L. Okay, so now earlier the direction of current is this, and now the all the energy having all the energy stored in the L is dissipated. So what will be the direction of this I naught when there is no L? I mean L is all the stored energy is dissipated into this R. Then the circuit will look like only this. So only this R is there and this E is there. Now no L is there because the role of L is over, no stored energy. Still we are focusing on this I naught. So this I naught based on this plus sign is definitely minus E upon R. That's why the I infinity is what? Minus E upon R, and the I not the initial value. So in this case, I mean when we are talking about this duration, so what is the initial value of current? This is the I max. So the initial value, that is the initial value is it is I max, and the final value is E upon R. This minus and this minus makes this plus, and this is E to the power minus t upon tau. So we will get this equation, and at t is equal to capital T, means at the end of second cycle your I naught will be I min. So you can see here at t is equal to capital T, at t is equal to capital T, your this I naught will be what? It is reaching to this I min. So we can put the value of that I min here, and we will get this equation. Now we are having these two equations, so we can calculate the value of ripple current, which is the difference of I max to I min. And after simplification, we can get these two equations also. And we can see if we increase the value of L, then the definitely ripple current will decrease. Why? Because if you increase the value of L, the difference between the I min and I max will be lower, because the tendency of L is to maintain the current through it. If you are increasing the L, your I min and I max, the difference will decrease and the ripple will be decreased. And I naught average throughout the operation is basically V naught minus EB upon R. And the freewheeling diode, this is very important. When the freewheeling diode will work, the freewheeling diode will only work when the chopper is off. When the chopper is off, so the freewheeling diode current through the freewheeling diode is nothing but the I naught current, and this I naught current is we can say this is the current through the freewheeling diode when the chopper is off. So this is the average value of current into T off upon capital T, because it is working when the chopper is off. So D off upon capital T means what? 1 minus alpha, and IS average means the supply current is the I naught into alpha. So this is the one mode of operation. And in the next video, we will see the discontinuous conduction when the RLE load is there. This case was the continuous conduction, in the next video we will see the discontinuous conduction. On the basis of current flowing through load, I can categorize it as continuous and discontinuous. So you can see that current is the continue over the 0 to t. No discontinuity is there. Means here we are using large size of inductor. When we are using the small size of inductor, it will dissipate all its energy before the before this coming to this point. Okay, means here somewhere here it will dissipate all its energy. So what about the rest of the time? The current will be zero. So that is the case when the discontinuous conduction we will see in the next video. So thank you for watching this video.